So in this my last lecture, I'd like to introduce several recent developments of application of this holographic entanglement entropy. So these are three topics I'm going to explain, probably 20 minutes, 20 minutes, 20 minutes. First one is about application to physics of thermalization, which is dual to black hole formations, and also application to Fermi surfaces. Fermi surface is very important object systems in condensed matter physics, which describes some metallic phase, which is very important. And we'll see what will happen if we apply AdS CFT to this Fermi surface physics and from the viewpoint of entanglement entropy. And finally, I'd like to discuss holographic dual of BCFT, which is boundary conformal field theory, which means that conformal field theory defined on the manifold with boundary. And I'd like to explain how to construct this holographic dual in the purely gravitational viewpoint and how this entanglement entropy plays a very important role in that construction. So let me start with thermalization. So thermalization is, of course, time-dependent phenomenon. And so we have to consider time-dependent setup of AdS CFT, which is sometimes, calculation is very complicated. But still, we have a very clear picture, which is that black hole formation in AdS should be dual to thermalization in conformal field theory. So black hole has a temperature, and this subcreation of temperature means that the system thermalizes. In temperature increases. So there are several explicit examples, and especially this Chastre and Yaffe and Bacciari and Minwara, and there are several also calculations how to construct such a black holes, time-dependent background formation of these black holes. And the simplest case of this thermalization is recently called so-called quantum quench. Quantum quench means that we have some one parameter, some mass parameter. We have some mass parameter or any coupling constant in quantum field theory, and we have some time evolution. And suddenly we shift the value of mass or some coupling constant. For example, if we start with some m0 to go to 0, then it eventually ends up with massless theory, which is conformal invariant. But this state, because this procedure injects some energy, so now it leads to some excited state in conformal field theory. So we can describe some interesting excited state in conformal field theory, and we can consider its holographic dual by using AdS CFT correspondence, and especially studied from the viewpoint of conformal field theory by this Calabrese and Cardi, so series of papers. So there, if we consider some AdS CFT dual, then immediately you find some following puzzle. This is about puzzle about entropy. So von Neumann entropy is always takes the same value if we assume unitary time evolution. So von Neumann entropy evolves this unitary matrix like von Neumann, following von Neumann equation. The entropy stays the same value. So if we start with some pure state, then it ends up with, again, pure state. That means entropy is always vanishing. But on the other hand, if we consider this kind of excitation or thermalization, we end up with some black hole formation. So black hole has we know that black hole has some entropy, so entropy is somehow productive. So these two, this microscope viewpoint seems to be naively, seems to contradict this very intuitive picture based on holography. So this kind of puzzle should be distinguished from the famous paradox, which is called black hole information paradox, which means that we have some start with pure state and black hole formed by this very heavy pure state, some matter, some material from some black holes. We start with pure state, but eventually it emits some thermal radiation, which is Hawking radiation, and naively end up with mixed state. But here we take into account the quantum effect of this Hawking radiation. But here we just talk about classical things. Just gravity side is totally classical, just purely classical black hole formation. So, but actually this is not so difficult to resolve this puzzle, especially by using entanglement entropy, holographic entanglement entropy. This is worked out with Arastia, Palacio, and Lopez paper, and also our independent paper with Gajin. And the upshot of this resolution is that, so both sides is actually not contradicting. And non-vanishing entropy appears only after cost-grain. So black hole has a non-vanishing entropy, but just because we do some cost-grain. And on the other hand, von Neumann entropy itself is always vanishing in the presence of black hole. For normal entropy means really, literally microscopic entropy. Just to consider trace law log rho for total density matrix without doing any coarse graining, then it always should be vanishing, even if we have some black hole production. To make this, to explain this from the viewpoint of AdS CFT, so first let us know, this already I explained in previous talks, and so total entropy, so just if we take some thermal entropy, we can express this thermal entropy, just difference between SA minus SB, assuming that A covers total space-time. We take the limit so that A covers total space-time. B goes to 0, in other words. So there, very subtle area of divergence cancels out, and it just ends up with total thermal entropy. So this is always true. So we'd like to look at this quantity. And what we have to show is that actually total entropy should be vanishing. So we want to claim that SA equal to SB. But this is just equivalent to pure state condition. But anyway, we would like to confirm this equivalence, this equality in holographic entanglement entropy in this black hole formation. So this is very some cartoon of black hole formation. So we have this time axis, and this is the AdS boundary. So this is a radial direction. This circle is sort of AdS boundary, but we can generalize it into any dimension. So here, we excite the system. This quantum quench happens, and black hole formed. And eventually, it just approaches to the static Schwarzschild, for example, Schwarzschild black hole. And now, we take some particular time slice, take some time, and we consider some subsystem A sitting here, and subsystem B is opposite one, it's complement. And we are interested in SA, time-dependent SA. And as I explained a few days ago, so the one description in this time-dependent background is using this covariant formulation of this entanglement entropy. So this is time-dependent. That means we have to take into account Lorentzian geometry. So we cannot literally take minimal area surface because it's Lorentzian geometry. So we have some light-like direction, which is 0 area. So what we need to do is take extremal surface, which is homotopic to this A. Homologous to this A. So there is a topological condition. And so and of course, we assume that this boundary of gamma A is equal to gamma A as a boundary of A. This condition is appears again. And we restrict such extremal surfaces, but if sometimes we have several candidates like this case, and then we take finally minimum value. We pick up minimum value surface. So if we do that, we can find the following result. So we have this surface A, this is subsystem A, and subsystem B is sitting here, and these guys are homotopic to each other. So naively, this gamma A corresponds to A, and gamma B corresponds to this B. This is true for static black hole case. But this is no longer true in this time-dependent case because we just assume this condition. So this gamma A is okay, but this gamma B can be smoothly deformed into gamma A because we can go this way. There is nothing here, so we can go this way. So we can smoothly modify, deform this gamma B to gamma A, and then gamma A is clearly have a smaller area. So that means that for SA, we take this gamma A, but also for B, we take this gamma A. So in this way, for both cases, we get same minimal, this extremal surface. So in this way, we can clearly show that this is true in this kind of geometry, this time-dependent background, if we assume this time-dependent formulation, covariant formulation of entanglement entropy. So both A and B correspond to this surface. And we take this minimum surface area. So in this way, we can show this A equal to SB, and that means difference is total entropy, so total entropy is always vanishing. So in such a pure state, even if we have some black hole production, total entropy is always 0, but that means total entropy is not that useful to detect black hole formation. So instead, we can look at just one copy of that, just one SA. Just we take entanglement entropy to probe black hole entropy. So entanglement entropy is a good probe of black hole formation. Indeed, as you can see here, it's wrapped on slide some parts. So this contribution can be easily detected by just even numerically calculated entanglement entropy. So let us note that in time-dependent black holes, the definition of just total, black hole entropy itself is not that unique because we don't know how to specify time slice. So we have some time slice on the boundary where we have a flat space, but we don't know how to extend it into the bulk. So there are infinitely many different ways to take some time slice. But entanglement entropy is uniquely defined, as is clear from the von Neumann entropy definition. So we can have some definite quantity. And also entanglement entropy at the same time trace out some part of the space. That means we are automatically do some coarse graining procedure. And this is the reason why we get some non-trivial result for black holes if we look at entanglement entropy. But if we look at the thermodynamical just von Neumann entropy, then it doesn't change. It's always 0. So is this clear? You come. Question? Yes.
So if you have an internal black hole, then you cannot go through this.
Exactly. Yeah. Exactly. So in that case, it's different. Yeah. There is a sum. Any question? Okay. So now I'd like to look at more in detail of time evolution of entanglement entropy. So there's so this is mainly review of what people have been done. And so this Calabrese-Cardy first consider this 1 plus 1 two-dimensional conformal field theory and how this entanglement evolves in time evolution and the time evolution. And so they find a very interesting rule. So this can be applied to any conformal field theory. Just use bilateral algebra with central size C. And the result looks like very simple. So if we have some time evolution, so here quantum quench, this excitation happens. And linearly, entropy always linearly increases, and then eventually approaches some constant value. And this constant value is just thermal entropy. So final system has some effective temperature, and this increasement of entropy is just equal to thermal entropy. And this linear growth actually also suggests that everything becomes relativistic. So information expands in a relativistic way. So we have a length L system. If we consider length L system, the time which we need to make everything thermal, this delta T, this thermalization time is L over 2. This is the time where assuming some particle sitting here, and at the speed of light, it goes to end of this. So this expanding time is exactly this time, this delta T, where this is some thermalization time from the viewpoint of entanglement entropy. So this is consistent with this relativistic nature of conformal field theory. And we can confirm this in holographic calculation, again done by this Alastia, Balcio, and Lopez paper, very excellent paper. So they compute this kind of time evolution of entanglement entropy in this AdS3 black hole formation. They're typically described by bidirectional black hole. So it takes a very simple form. This is the mass of black hole. And if we assume m equal constant, then this metric is just equivalent to standard BTZ black hole, static AdS black hole, but it's now time dependent. So it suddenly we can quench some way. And then, so we can follow some time evolution of this entanglement entropy, and it looks like indeed real increasement. It depends on different subsystem, but it looks like nice agreement with this result. But also, at the same time, holographic approach has an advantage that we can increase the dimension. So this approach can be this field theory approach only can be applied to 2 dimensions because we use infinite many dimensional bilateral algebra, some conformal map technique. But the holographic approach can be done in higher dimension. And there are several works, excellent works that have been done for higher dimensions, Albert Johnson and Baras-Brania and collaborators. And they did this kind of calculation for higher dimensional case. But then something new ingredient appears, so we can choose many different kinds of subsystems. One subsystem is this kind of strip, also I explained a few days ago. And strip, another one is a round disk. So this case is everywhere. So from this point, it's everywhere. Distance is always L, but this case is non-trivial. If we go to this particular direction, length is infinite, but if we go to this width direction, it is just L. So after computing this kind of analysis, they find that summarization time from the viewpoint of entanglement entropy is much larger than L over 2 in this case, but round case it's almost same as L over 2. And this is consistent with the picture. So here it's everything. From here, the information expands at the speed of light, and it just reaches by this time. So this is L, and maybe this L over 2, I should say, sorry, L over 2. And here, it's larger than that, because if we go, sometimes we go this direction, and sometimes go this direction. It takes a longer time, and everything seems to be consistent with this idea of conformal field theory and the information expansion. And so at the same time, it is interesting to look at explicit calculations from the viewpoint of conformal field theory. And so just now forget about holographic river, just consider some explicit calculations. And here I would like to show one example where we can do computation analytically everything, and even we compactify some one spatial direction. So this example is 2D free Dirac Fermion. The good point, technically good point of fermion is we can bosonize this fermion into some bosons, and then this twist operator, which I explained a few days ago about to describe this replica method of entanglement entropy, can we just realize some vertex operator using bosonic representations. Everything becomes free field calculations. But of course, this is free field CFT, and the interpretation from the viewpoint of holography is very subtle, and at least it should correspond to some very quantum region of quantum gravity. So it's far from the standard AdS CFT, classical AdS CFT region. But in this case, we can do the calculation exactly, and especially, so this, after this quantum quench, we can approximate the initial wave function by so-called boundary state. Boundary state is a state in a boundary conformal field theory. So we have some boundary. And we preserve one copy of Virasoro. We have some upper half plane, and at this boundary, we preserve one copy of linear combination of Virasoro algebra. So we have two Virasoro in the bulk, but at the boundary, we have one copy of Virasoro, and this is the definition of boundary conformal field theory, and this state is represented by, from the viewpoint cross string, it's described by this boundary state B. So this B, and we need to put some regulator. So this H is Hamiltonian of this total system, of this CFT, and epsilon is some regulator. So the whole high energy, so very high energy, this factor really dumps. It goes to 0. That means nothing. Ground state is just trivial vacuum. But the whole low energy excitation, it looks like boundary state. So this is very, this is consistent with this kind of mass quench. So for mass quench, this change of mass is assuming 1 over epsilon. This delta M is now assuming 1 over epsilon. Then if we assume the higher energy scale, then this kind of quench doesn't mean anything. That means everything stays the ground state. But if we look at low energy scale, which is smaller than this scale, then this quench has a very strong meaning. And in the infrared, it goes to some infrared fixed point, and which is described by this boundary conformal field theory. So by using that, we can compute everything. And I don't write the details, but in the end, we can get this kind of nice expression. So this looks like very similar calculation of what I explained a few days ago about this finite temperature and finite size calculation. But now everything written in terms of nice periodic function, this theta function. That's different from the previous torus calculation. So, but anyway, so we get some theta function representation, and this manifestly satisfies SA equal to SB. So region A is size sigma, that 2 pi minus sigma is the region B, size of region B, and this manifestly, this equality is manifestly satisfied. Also, but unusually, this is peculiar to this free field theory. We have some very short recurrence time. This is just time pi. If we t plus pi, then this result is very, but this is very peculiar to free field theory. Free field theory, conformal dimension is really, it takes in some integer, some sort of integer, so this kind of recurrence time appears. So but anyway, so if we plot this, then we find following behavior. So this is time evolution, and this is a finite piece of entanglement entropy. So it's short recurrence, but anyway, so it first increases. This increase behavior is same as this one I explained. This is just agree with this kind of. But now the point is that we are taking into account this finite size effect. So this periodicity in sigma direction is 2 pi. So it actually reaches at some point, and this is thermal entropy. Thermal entropy is finite because size of system is finite, and it's going down actually after it reaches, and it oscillates in this way. So of course this is a free field calculation, but it is not that difficult to imagine what will happen in strongly coupled case. There, this time is much getting larger, and it's like Poincare recurrence time, something like very large time appears, and again going down. So that means some black hole is somehow created at quantum quench, but it shrinks and repeated somehow. But for classical approach, this time is infinite. But for finite n, and if we take the quantum corrections, this time should be finite. And in this way, somehow, black hole formation and evaporation.
What's happening here?
Sorry?
On the right, you have black hole creation.
Yeah, this is black hole.
And then it evaporates.
Yeah. And again, it evaporates, but that's waves are, but going back, this AdS, so it's coming back, and again doing that.
But there's no gravity picture anymore. This is very small.
That's right, exactly. It's a very toy model of this string.
So you said infinite time?
Yes?
You said infinite time.
Yeah, classical should be infinite time, yes.
You expect the recurrence time to be like n, I mean...
This calculation, it's not easy to do that. But yeah, exponential to n square or something. Yeah, just as usual. I have it.
You have any reason for that it might be like that in this case?
No, just based on the standard, intuition of Poincare recurrence.
No, the reason I'm asking is
Yeah.
there is a calculation by Shi Yin and his student of, they compute something slightly different, torus two-point correlation functions in the Wn minimal model CFTs, which essentially are like n-free fermions. And that is believed to have a holographic dual. And they find a Poincare recurrence time which is scales like n.
I see. Not the exponential, right?
Square.
Not the exponential.
Not exponential.
Yeah. So I think in this case we can do it symmetric product CFT, but that gives I think order n, not the exponential, but just n or something. Yeah. So but that's not satisfactory, I should say. Yeah, from the people standard AdS3 CFT2.
But maybe it's related. Maybe AdS3 it's simpler because there are no gravitational modes.
Maybe. Yeah, that's a good point. But sorry, I don't have. Further. That's a very interesting point to explore. So okay, so this is so I finished this summarization issues. And are there any questions, comments? Okay, so yes.
So this slide that SA minus SB is a more interesting quantity than
Sorry, SA minus.
the growth of more than the growth of SA. In the slide that you showed in the black hole case, SA is not equal to SB. More than the growth of the growth of SA minus SB is more interesting.
No. SA minus SB is not interesting because it's just corresponds to some thermal entropy, and it stays the same. I'm assuming A goes to B goes to 0 limit, then it stays the same. But SA itself is interesting. SA itself has a non-trivial time dependence.
But SA minus SB also can have some interest.
Yeah, if you assume SA is somehow some partial region, then interesting. But what I talked before is that we take A try to cover everything. In that limit, it's not interesting. It's always stay the same value.
Yes, but if SA is somewhat partial region, then the growth of SA minus SB. So what I was basically going to ask is, this SA minus SB has some direct analog in theory. Because SA minus SB shows that the state has been somewhat post-grained.
Right, yeah, okay, yeah. So if we choose A is some middle space, then interesting.
Yeah, so
Yeah.
does it have some direct analog in richness of the state or something?
Yeah, but it has a definite quantum mechanical meaning. It's trace out some part. In that sense, this is some coarse-grained entropy. But I cannot say more than that. It just go back to definition of that.
Can you show that SA always increases as a function of time?
Sorry?
Can you show that SA always increases?
No, not completely increasing. It's increasing, but sometimes decreasing.
But in gravity, I mean, this is no longer.
Okay, gravity. That's excellent. That is related to in gravity. That's related to null energy condition. You can show it. Mm-hmm. Yeah, there are several works. We also did that works. Okay, so. Okay, so I need to quick. Okay, so now I'd like to also mention about the development about Fermi surfaces. This is something I already explained. So in the presence of Fermi surface, area rho is somehow violated logarithmically. It is L to the d minus 1 log L. And L, so this is somehow, in condensed matter literature, people write this way. L is some just integer. It's the size of lattices of A. So, but then we can rewrite this large L in terms of continuous value. L is a real length, and A is a lattice spacing. So we can switch between them. And this property are shown particularly in the case of free field theory. But recently there are several discussions and also some real numerical calculation done by this Berkeley group that even non-Fermi liquid, so non-Fermi liquid is somehow very strongly coupled Fermi. So if we have some Fermi, assuming Fermi surface, but very, very strongly coupled, then there are no longer some quasi-particle picture, which existed in Landau's Fermi liquid picture, but there are no such a quasi-particle picture. And such a case is called non-Fermi liquid. And so one example is spin liquids or some strange metal phase in high TC superconductor. Unfortunately, I don't have enough time to explain some of this condensed matter background. But so that kind of example is studied numerically, and still people confirm that this logarithmic violation true. But in this kind of calculation, this is just really condensed matter. Everything is made from lattices. So they are assuming this condition. So UV cutoff is the same order of Fermi energy. So assuming this finite size of Fermi surface, that means exactly this condition. This is something we don't want. So UV cutoff is scale same as Fermi surface energy. So we are actually interested in UV cutoff scale is much larger than Fermi surface energy. In this case, it is very just naturally, this part is reduced to just constant finite term contribution. So we have this divergent piece is just for area rho, not modified by logarithmically. Divergent part is the same, but this logarithmic part appears in a finite part of entanglement entropy. So L is the size of the system, size of the subsystem, and Kf is the Fermi energy, and again log term also appears. Sorry, yeah, good. Sorry, yes, I should say d minus. Sorry, I'm mixed with some other convention. So I'm sorry. This is d minus 1. So this is just proportion to area. And so beyond what we'd like to do is to just see whether we can realize this kind of behavior. So this is something we use as an input. So we just assume that, we just claim that if we have a Fermi surface, this should be true. And we use this as an input, and assuming that all physical quantity can be calculable in classical gravity limit. So this is something we usually assume in AdS CFT in the classical limit. So we just take large Tofuto coupling limit and large N limit, and we just keep reading order. But in other words, from this Fermi surface language, there are order n square contribution from Fermi surfaces. Now this is an assumption which we work with here. So then we can assume the following metric ansatz. So this is a time component is somehow Fz, and Zz is the component, and this is a space component. I'm assuming 2 + 1 dimensional system dual to something like AdS4 CFT3 setup. We can easily generalize into higher dimension, but let us assume this way. And then, so this is a rather general metric, so we can just use diffeomorphism to fix this coefficient z square, and also some mixed term is also eliminated by coordinate transformations. And what this behavior of entanglement entropy tells us that this function z should be proportional to z square in the infrared. Z goes to infinity is infrared in my this same as my information 0, and it's like this. Factor is like this. It shrinks 0. And Zf is some energy scale because everything should be dimensionless about Z. This is identified with some energy scale of Fermi surface, Fermi energy. And indeed, we can confirm in this case. In this case, and holographic entanglement entropy looks like L log L. So assuming this is D minus 1, and we just replace this 1. So L log L behavior appears. And we can also analytically show in particular choice of subsystem that this should be true. So this is the input. But unfortunately, this Fz is not completely fixed. So it's not easy to derive any dynamical quantity like entropy or specific heat. But there is a clever idea to overcome this. This is a use of null energy condition. So in any physical sensible holographic dual, we should impose this null energy condition should be always satisfied, This means, roughly speaking, this energy of some system should be positive. So otherwise, we have some ghosts and very funny excitation. This should be always true. And this is something we want, we use to prove holographic C theorem. So this is something very good condition. So then ZZ is already seen. If we have Fermi surface, this should be Z square. And Fz, we can assume just any power of Z. Then this null energy condition claims that this M should be greater than 2. So we just have a bound, but this bound has something interesting, tells us something interesting. So if we rewrite everything in terms of specific heat, we can just easily imagine what will happen if we heat up this system, just standard assuming horizon, then only this information is needed to find some specific heat behavior. Some coefficient I don't know, but it's how this specific heat behaves against this temperature. So temperature dependence. And this coefficient, this power of this temperature, T to the alpha, this alpha turns out to be 2/3, less than 2/3. This condition is actually very strong, and so strong that it excludes standard random Fermi-Liquid. If we have random Fermi-Liquid, specific heat should be always linear, because everything is just approximate 2D CFT, as I explained a few days ago, and 2D CFT are always linear specific heat appears. So that means random Fermi-Liquid also is not possible in this limit. So inevitably, we have some other thing which is called non-Fermi-Liquid. But there are, if you are familiar with this recent developments of AdS, CMT, or some condensed matter application, then one might know these nice examples of this MIT group, and also something this using emergent AdS2 geometry, and also something called electron star, worked at Hartnell-Polchinski, Silverstein-Thom, and Hartnell-Kapastar. And there, people construct a very interesting candidate of non-Fermi-Liquid or Fermi-Liquid. But our analysis does not include this kind of configurations, because to deal with this configuration, in this system, Fermi surface appears only order 1 or less than planar order. So what we are assuming is that Fermi surface realizes at leading order of n square contribution. So in that sense, this kind of model is not included in our case. That's the reason we have very sharp results that there are no random Fermi-Liquid. Also, there are very interesting some coincidences. So this Fermion shows that among this configuration, so among this metric, so this is bound, but first of this 2/3 is some special value, and only when this 2/3 realize, there is a situation is less singular, no curvature singularity. But even if we have curvature singularity, it is okay because we can just heat up the system, and if we have a horizon, everything becomes regular. This is a very similar situation like so-called Lifshitz background. There again some singularity appears, but if we heat up, there are no problem. But when 2/3 case, everything becomes very good. I mean, singularity is resolved somehow. And also, interestingly, so if you look at real material, there is a famous example of this very anomalous example among this non-Fermi liquids, so strange metal phase, which is described by this compound, yttrium and so on. And this case, precisely experimental data predict these 2/3. And finally, even just theoretical approach to condensed matter physics, and if we take large limit, but unfortunately this large limit means slightly different. This n is some n of flavor, number of flavors, and then again 2/3, some 2/3 value. And in this way, maybe these things are related. Then it's very exciting to have this result. But at least AdS CFT tells us that in a really strongly coupled system, we cannot get any random Fermi liquid. And we can also, this is a bit technical comment, but we can embed this. We just worked out in a general formulation, just based on generic metric, but we can embed into some particular background of this effective gravity theory, which is Einstein gravity coupled to Maxwell field and scalar field with some potential. And this potential and so on should behave this way. And also later it is pointed out by Sachdev and Swinger and collaborators and this Kashira and collaborators that this background is also interpreted as some modification of Lifshitz background, or this is called some violation of hyperscaling. So this Lifshitz background is this part. These are some anisotropic scaling invariance. But we have additional factor which breaks this scaling invariance. And there, for example, specific heat is modified. So usually d over z is a dynamical exponent, but slightly modified by this term called theta. Okay, so these are my talk about Fermi surfaces, and I move on to the boundary conformal field theory. So I'd like to ask a few questions.
You said that alpha is equal to 2 by 3 is the most anomalous example. So why is it most anomalous?
Sorry. Okay.
Ian, can you use your microphone?
Why is alpha is equal to 2 by 3 the most anomalous example?
It's in condensed matter physics.
Yeah, why is it most anomalous?
That is just from phenomenological thing. If we look at all, just study known examples of, this is something called a heavy Fermion system.
In the sense it's most distant from 1 or something.
Exactly, yeah, different from that. Yeah,
but you said that alpha has to be less than 2 by 3 by holography. So it's
yeah. But that is true. But also, 2/3 is very special value that this holographic background becomes more smooth.
Okay.
Sorry, how is this related to what you said earlier? Is alpha the same? Is alpha equal? This alpha is not the same as your earlier alpha, is it?
No. Sorry, it's different. Sorry, alpha. Sorry. So this alpha. Sorry, I'm sorry. This alpha is different. This alpha is just some value which takes this between these values. Sorry. Yeah.
And so if the earlier alpha equal to 2 by 3, does that corresponds to?
That corresponds to this one.
So that corresponds to theta equal to.
Right. Yeah. So I'm sorry. I'm switching. So.
And when you change alpha, then you go to the other.
Sorry.
If you change alpha, the earlier alpha.
Yeah.
If it is greater, if it is less than 2 by 3.
Yeah, but still same, because this alpha is only determined from the behavior of this function z, and alpha related to this m.
Okay. I see.
Sorry, yes, confusing.
But this class of solutions that you had.
Yeah.
In your later.
Yes, this one.
Yeah. So this class, this corresponds to only alpha. M. What is the value of m here?
M. Okay, this m is okay. So here m is related to z. I think z and theta. I think its relation is not trivial. It's some linear combination of z and theta. always. There are two parameters, z and theta, that is mapped to m and m.
That's mapped to m and?
M and alpha in previous.
Alpha is d minus theta over z, right? It's the power of t in the specific heat, is it?
Yeah, sorry, yeah, this is exactly alpha. Yeah, yeah, this is exactly alpha, yeah. Yeah, yeah.
One thing I'm talking about the rules of the game here, because for me I'm not completely clear. So you have this Fermi surface, you know, from condensed matter that is the theory of Holographic Construction, and then you just cook up an AdS metric which reproduces this. This is just, you cook up this metric with some kind of general requirements.
Yeah, yeah, yeah.
And then you try to see what is the AdS metric that will reproduce this entropy behavior. But there is no other constraint on
it's a constraint is this null energy condition.
this general non-singular, you know, yeah, but
Yeah, we didn't impose, yeah.
this is like, okay.
Yeah, if we impose singularity condition, these two stars is really selected.
Yeah, but these are very generic conditions on the metric, right? That we have a sort of reasonable solution of gravity, but there is no other input but that.
Yeah, this is really phenomenological construction. Okay, so by using rest of time, I'd like to explain the holographic dual of boundary conformal field theory, and it's how this entanglement entropy plays important role. So, yeah, so the first question I'd like to ask is what is a holographic dual of conformal field theory which lives on a manifold with boundary? And if symmetry, the part of boundary conformal field theory is preserved as a boundary, this is called BCFT, boundary conformal field theory. So conformal field theory has a symmetry SO, d-dimensional conformal field theory has a SO d comma 2. This is a Euclidean symmetry, assuming Euclidean CFT. And it's part of the subgroup of that SO d minus 1 comma 2 is preserved for boundary conformal field theory. And so there are several earlier studies about this kind of constructions, and the idea is already briefly mentioned in the paper by Kalch and Randall, and also similar but different construction of CFT with this symmetry. It's called Janus CFT or interface CFT. It's discussed by these papers. And but anyway, so let us consider the simple construction of this boundary conformal field theory, which and this is given by some just classical gravity viewpoint. From classical gravity viewpoint, we have this z direction, which is the same as radial direction of AdS, and this is a boundary of AdS. But we are interested in the holographic dual of some manifold with boundary. This is called M. This is lives on the boundary of AdS. But we totally cut it out as a part of a boundary. So here it's extended. It's just flat space, but we just pick up particular part of that. And then it is very natural to think that this region is dual to this kind of region, some inside the AdS. But we have to be, of course, careful about this construction. And we first show that everything should be consistent with this variational principle and so on. So this is a standard Einstein-Hilbert action. We have some curvature and matter, Lagrangian, and also we have boundary term. So this boundary term is inserted on this boundary, new boundary, which we call Q. So M is extended. Boundary of M is extended in the bulk, and this makes a surface called Q. And inside Q is defined to be M. So the claim is that the CFT, BCFT defined on this M is dual to gravity on this manifold M. And N has a boundary, which is Q, and there is a boundary term on this Q. So this is a standard Gibbons-Hawking term. And we have to impose some boundary condition on Q. And usually, at the AdS boundary, we just impose Dirichlet boundary condition. But instead, Q, on Q, we impose so-called Neumann boundary condition, which is just given by taking derivative about the variation of this metric on Q, this induced metric on Q. And which leads, this Neumann boundary condition on Q leads this way. KAB is an extreme curvature, and K is its trace, and TAB, Q is a boundary energy stress tensor. We assume some matter is localized on this Q, and its effective energy stress tensor is described by TABQ. And conformal invariance says that this should be proportional to HAB, otherwise somehow we don't have nice symmetry.
Sorry, Takashi, Q is fixed, or it's free to fluctuate, or it's...
Yeah, it's free to fluctuate. Yeah, that's good. Yeah. So Q is fixed by this condition. And we only specify this boundary of N and M. We only fix geometry of M. And we also even didn't any mention about the expression metric in the bulk. Sometimes this is modified from standard AdS Poincare metric. Because this Q back reacts. Q has some tension, then Q back reacts to the metric. And also the position, the location of Q is also fixed by this Neumann boundary condition. So everything is back reacted. So in general, it's quite a rather very complicated problem to fix this. But there are several simple examples. So for AdS slice, so we take the following AdS slice. So AdS D plus 1 is sliced in terms of AdS D with one radial coordinate, which is called rho. So hyperbolic cosine and log over R square appears. So this is a very familiar parameterization of AdS space. And this is a boundary of AdS, and this is a Z direction, this Z direction. This is a boundary of AdS, but now only keep one half semi-infinite part of the boundary, and this part is get leaded out. So forget about this region. So then the bulk region is this region, and this surface Q is extended from this boundary. And you can choose many different Q, but it is true that in this case, to keep this boundary conformal invariance, this should be some straight line. But this angle can be changed. This angle is related to this tension of this boundary Q. Q is related to this rho star. Rho is this coordinate. Rho is this coordinate. Rho is minus infinity here. It's go this way and plus infinity. This is 0. Rho is 0 and plus infinity. And we pick a particular rho so that we have some one boundary. And later we will see this rho, this parameter T or rho star is correspond to boundary entropy or G function of this dual boundary conformal field theory. So the point is that we just pick up this region and claim that this region, gravity in this region is dual to the conformal field theory on this manifold M with this boundary. So now we'd like to compute the so-called boundary entropy. And boundary entropy is first introduced by Affleck and Rudolph. And this measures the degree of freedom at the boundary. And this is some analog of central charge, but we are interested in some theory with boundary, and especially degree of freedom, which is on the boundary. So this is measured by boundary entropy. And this boundary entropy is shown to be monotonically decreasing under RG flow. This by originally this conjecture by Affleck-Rudolph, but proved by freedom connecting. And this is much like the homology of C-CERN. This is called G theorem. And then one should ask how to compute this G. So one way, there are several ways, but one simple way, just take disk amplitude. So this S boundary, this is a boundary entropy, and alpha parameterize different boundary condition. So we have some disk, and this 2D conformal field theory, and we have some one boundary condition which fix this. And this is parameterized by alpha, and this we like this log G, and G called this G function. They are almost equivalent, just relation of exponential. And this G function is given by this way, by using boundary state formalism. This B alpha is boundary state for this boundary condition. This gives disk amplitude, and log of disk amplitude is this boundary entropy. But this has some problem that we have to fix this normalization. Then it is sometimes convenient to look at cylinder amplitude. So we have two boundary. Then cylinder amplitude written in terms of boundary state like this. B alpha exponential H is Hamiltonian, and extend this way, and B alpha. And it's in the large L limit, infrared limit. It's factorized this way. G alpha times G beta, which contribution from this boundary and some this zero energy part. So, and we can pick up this value, G alpha, this way. And the final method is to look at entanglement entropy. So we have, so far, we only discussed entanglement entropy on some closed manifold, but it is also possible to consider entanglement entropy on some manifold with boundary like this. So this is the Euclidean time, some time, and the space direction is like this direction. And we have a boundary here, and it's semi-infinite this way. And A is, subsystem A is somehow we can take to be this, and the other part is B. And assuming this length of A is L. And then, so of course we have this contribution, C over 6 log L epsilon. And we have this contribution. And, but in addition, there is some constant term. And this constant term is identified with this boundary entropy. So this is also mentioned, derived in Calabrese-Cardy paper. So in our setup of boundary conformal field theory, holographic dual of boundary conformal field theory, is we can just compute this as some geometric length. This is using minimal area surface formula, area formula. And this is basically what we do is to compute this length, integral in this direction. And so if we end up with here, it is rho star equals 0. So if we increase rho star, then this angle increases, and accordingly, this contribution increases. So this part is identified with boundary entropy. This part is the same as previous calculation. And also we can derive in other method like cylinder amplitude, also disk amplitude. And all of this calculation leads to the same result, this rho star to the n. And we have to take twice of that. So we have this result. So here, this case is, this is cylinder, so we have two contributions. That's the reason we have 1 over 2, but it is 1 over 4, and 1 over 4 appears because we just pick up one boundary contribution. So, if we write this in some picture, so holographic dual of disk. So here we said some calculation of partition function on disk. This disk is dual to some part of the sphere inside. This is the AdS space-time, but we cut it out, and we only keep inside this region. This region is N. And also the cylinder calculation, we need to go to the high temperature phase. So we have some black hole, and the black hole horizon is sitting here, and we have this boundary Q, and we integrate out this part. And this leads to these calculations. And so by using that formalism, it is possible to also prove Z theorem from the holographic viewpoint. So this can be done. Good point is this can be done in any dimension. And so, like in a holographic proof of C theorem, we can impose null energy condition. And this is a Poincare metric, and we assume that this some boundary is parameterized by boundary Q is parameter x equals xz, and embedded in this space-time, and this null energy condition says that. So we have this space-time, and this is a z, and this is x, and we have some boundary, this boundary Q, and this parameterized by x equals xz, x equals xz. And so in the end, this condition says that the second derivative is negative or 0. Of this x is negative or 0. And so we can define this holographic g function in this way, some particular combination of xz over z, and we take derivative of that. Then we find that. So this derivative of that is negative because if we take again one more derivative, it is negative, and it starts with 0, so it's always negative. So we can show that this derivative of z derivative of g function is negative. So this means that in this evolution, if we go into large length scale, it's always decreasing. So this is our holographic Z theorem. So this predicts that somehow Z theorem can be generalized into higher dimensions. For example, if we look at AdS4 BCSC3, so three-dimensional conformal field theory with boundary, So what this tells us is that some contribution, this contribution is somehow monotonicity, has a monotonicity behavior. So this is something unusual contribution. So in three-dimensional conformal field theory, we don't have any central charge. Although dimensional conformal field, there's no central charge, but some logarithmic term, logarithmic divergence. I removed divergence, but this comes from logarithmic divergence. And RB is a radius of this subsystem, this region M. This cutted out surface, this region M. And so it's logarithmic scaling, and this coefficient non-vanishing. So this is unusual because there are no conformal anomaly in 3 dimensions, but in this case is different because we have also 2-dimensional boundary. We have 2-dimensional boundary. So that means that we can somehow define some analog of central charge in 3 dimensions. So if we have boundary. So if we have boundary, we can just, this RB is just this radius. We pick up this region in 3-dimensional conformal field theory. And we are talking about holographic dual of this ball with radius RB, and we take derivative of RB and log of partition function, and this should be related to some trace anomaly. And this should be, so as we do for central charge, we can somehow define boundary, effective boundary central charge in terms of AdS curvature and this low star. And the holographic G theorem says that the C theorem is, holographic G theorem says that actually this quantity also is monotonically decreasing under RG flow because low star satisfies that condition. So this is very interesting suggestion. So this is only, at least we only show that this result for AdS CFT case and the classical limit of AdS CFT. So it is not completely clear, but it is interesting to see if this kind of C theorem, boundary central charge C theorem, is true for any 3-dimensional BCFTs. Okay, so, and also finally, I'd like to comment on some time-dependent solution. So this is a time and space, X, and we are interested in AdS3 CFT2 setup. And so now we assume that there are 2 regions and with boundaries. So region A has this boundary and region B has this boundary. These are just boosted trajectories. This, if we go this way, this is a Lindora observer. And this kind of configuration is obtained by just taking analytical continuation of the this configuration. So this spherical configuration. This is a Euclidean time and this is a Euclidean space, but now we take analytical continuation and we get this one. Previously it's plus, but now minus. And this kind of configuration, the interesting thing is that the observer here is completely disconnected, causally disconnected from this region B. So if we send signal at the speed of light, it don't reach this region B. And we can easily to construct this holographic dual because this is the answer. So this region and this region is now connected inside the bulk. This is Z direction. So the boundary conformal field theory on this disconnected pieces are now just described by AdS, some connected manifold given by this. And there, this entanglement also plays a very important role. They are connected. Disconnected means that these 2 CFTs lived on A and B, they are entangled with each other. This entanglement entropy is just lead of this similar areal formula, which this just counts the length between here. So this region A and B is now connected in the bulk, and this length of this slot, width of this slot is correspond to entanglement entropy. If they are really separated, there are no slot which connect them, that entanglement entropy is 0. But if they are close to each other, they are connected by this amount. And after some coordinate transformation, we can map everything to BTZ black hole. And this is interpreted as some part of the BTZ black hole entropy. So this is a BTZ black hole, but this part is only covers some part of horizon. And this is a boundary Q in these setups. Okay, so these are all of my talks. I summarize conclusions. And so this entanglement entropy is connects with some wave function sometimes in condensed matter system to gravity metric. So this entanglement is area from the viewpoint of gravity, but it's a real Von-Neumann entropy from the viewpoint of wave functions. And this helps us to understand this wave function in terms of metric in the gravity side. And this entanglement entropy can characterize various phases of ground state, so CFT or mass gap or Fermi surfaces or topological some ground state or something like that. And also in odd dimensional conformal field theory, it provides an analog of central charge, which is missing in standard wire anomaly argument. Also, especially in higher dimensions, where the calculation gets very complicated in quantum field theory approach, this holographic calculation of entanglement entropy offers a very powerful way to calculate entanglement entropy for strongly coupled systems. Also, finally, it should be also helpful to understanding of this quantum gravity from the viewpoint of this quantum entanglement by using this AdS CFT correspondence. And I listed future problems. Some proof of this holographic entanglement entropy formula is area formula, and higher derivative correction and quantum correction are completely understood now, and hopefully in future, it's one of my corrections. And also, we should understand more about more microscopic description of this Fermi liquid or non-Fermi liquid in terms of AdS CFT correspondence. And also, generalization of non-AdS spacetime where we have mass gap or even changes some asymptotic geometry. There, sometimes we break some area law, and the understanding of that also very interesting. And finally, these two are very ambitious goal, which is some real reconstruction of this metric from entanglement entropy. So if this should related to metric, then we should somehow understand the Einstein equation itself from the viewpoint of this quantum entanglement. And also, this might help us to give some new formulation of quantum gravity in terms of quantum entanglement. So I think I will stop this. Thank you very much.
More questions?
Can you just elaborate on that last point about the analog of Einstein's equation?
Yeah, so, yeah, of course, I don't know the answer, but recently there are several interesting, sorry?
What is the
question, yeah. So, okay. So, I mean, so here we have Einstein equation which fix this metric, right?
Yeah.
So I'd like to understand the origin of this condition from the viewpoint of entanglement entropy. So entanglement entropy, from entanglement entropy, basically we can reconstruct the metric itself. So if we know entanglement entropy for any choice of subsystems, we can reconstruct the metric.
You know all possible minimum.
Yeah. So, and there, this Einstein equation should be play very important role. That is something.
So I have a question. I got confused by your discussion about thermalization. So you define the thermal energy as being the difference of SA minus SB when A covers the whole manifold, and you find that this is 0 after the black hole has been produced. But definitely the usual thermal entropy, which is the Bekenstein-Hawking entropy, is non-zero. So what's the relation between one and the other?
What I'd like to say is that definition of Bekenstein-Hawking entropy in time-dependent background is not unique. It's quite difficult. And if we start from this time-dependent black hole from 0 size, one answer is just 0, always 0. And because of the problem of this choice of time slice, and its answer is not unique.
So your definition is better motivated from the microscopic point of view?
Yeah, exactly. Just I'm using this microscopic von Neumann entropy. Then we have to conclude that its entropy is 0.
Any other question? Okay, if not, let's thank Takashi for the beautiful set of lectures.